All right, we've been talking about perpendicular bisectors. Now we're going to talk about a different bisector, an angle bisector. So this just bisects an angle. So this is the angle bisector theorem. So you know an angle bisector is a line, segment, or ray that bisects an angle specifically. So if a point is on the bisector of an angle. So we just talked about perpendicular bisectors, and that theorem was talking about if a point was on the perpendicular bisector. Now we're saying, okay, if you have an angle bisector and a point on that angle bisector, then it is equidistant, just like in the perpendicular bisector theorem, but this one is equidistant from the sides of the angle. So this really, we're talking about the same angle, so I'm going to change this to say the angle. So a couple things to make sure you realize here. When we have the distance between a point and a line or a ray, because that's what the side of a triangle is, remember, that's a ray. So the distance between a point and a line, which a line, again, an array, you can extend a line through that, has to be perpendicular. This is the biggest mistake you will make if you don't pay attention. The defined distance is from that point to that line, it has to be perpendicular. So we did that back in chapter 3. So if I had a line like this, so this is not a right angle, right? This distance of this line segment is not the distance between this point and this side of the angle. That's not the distance. This is not the distance. This is not, this is not, this is not. It has to be that perpendicular segment, the length of the perpendicular segment from the point to the line, or in this case, the ray. So you have to have that marking here, otherwise this is not the distance between the point and this line. So we're going to go ahead and give some names to these points so we can talk about them. Let's call this vertex B, and we're going to call this point right here A. We're going to call the point on the angle bisector D, and we're going to call this point C. So in our picture, BD, ray BD is the angle bisector. We can also say that line segment BD is the angle bisector, or we could say line BD is the angle bisector, because they're all one and the same, except that when you're talking about the line segment, you're only talking from here to here, so it has length. When you're talking about the ray, it starts here and goes on forever, and if you're talking about a line, it goes on forever in both directions. But all three of them are an angle bisector to that angle right here, which we have to call angle ABC, because now it splits it into two congruent angles. So that's why it's marked here. You have the arcs, one arc on each, to mark that they are congruent angles. So in order to use this theorem, the hypothesis is if there's a point, and we're going to call that point D, if D lies on the bisector of angle ABC, which it does. We know this is an angle bisector because of these angle markings marking them congruent. So if D lies on the angle bisector of angle ABC, and you have this as actually measuring the distance, so that means that AD is perpendicular to AB. So that's just saying that this to here is a right angle, so that this actually is measuring distance. And so we want the same thing over here to actually measure distance. So we need DC and CB to be perpendicular. So, and I'm just going to call it DC perpendicular to BC. And you could also put ray BC there if you wanted. It doesn't matter, because it's the same. It's going to be, we're talking about the same thing. So I have that saying that is the segments represent the distance of the point to the sides of the angle. So if all that is true, if you know this is the angle bisector and you have this point on there, and you have a line segment where it's perpendicular to the sides of the angle from that point, then we can conclude that those are equal in measure. So we can conclude that AD is equal in measure to DC. Now, in a proof, I probably would want to call this CD, because in order to prove this, again, surprise, surprise, we're going to use congruent triangles. So I would want to call that a CD instead. But for now, that's fine. So, and then I'm just, again, reminding you, recall distance from a point to a line is defined as the length of a perpendicular segment from the point to the line. So there has to be that right angle mark. If you're given something like this, you're told this is the angle bisector, and I give you something like this and ask you, hey, do you know if these two are equal in measure? You can't know. Even if they look like it, you can't know, because that's not what this theorem is saying. It's saying if the distance, so this is not distance, here to here is not the distance between D and ray BA. This is because it's the length of a line segment from that point to the ray, the side of the angle that's perpendicular. So you can't make conclusions about lines like the ones I'm just erasing there. But we can if those are perpendicular, which means it's the distance. Again, this is really easy to prove, so let me show you how we can prove this. We can just start out with that angle bisector there, so I'll just draw this off to the side. If we have a vertex of an angle, and we just have this angle, right? And we say, okay, this is an angle bisector. So we know that these two angles are congruent. So we'll just say B, and then we'll go ahead and put that D there. Now, by the perpendicular postulate, we know that there is exactly one line that is perpendicular to this line that goes through point D. There's only one that exists. So we can say that we're going to construct it. And we can say that, and this would be like drawing the auxiliary line, and we can say that we're going to say that that intersection is A, and that would be by the postulate that says that two lines intersect at one point. You know, there's lots of things embedded in there, and we know it's a right angle because we constructed this as a perpendicular line. We would do the same thing to the other side, and I'm just freehanding this here, guys. So we would do that same thing at the other line, and then again, we could name that point. And then again, we have the right angle. Now we can easily prove this because look, we have that these two angles are congruent. So we have the angle ABD is congruent to angle EBD, and that's because the definition of the angle bisector. So I'm not going to write that right now. And then we have that these two are right angles, so we'd have to say, hey, they are both right angles by either the definition of perpendicular, because that's what we constructed was those perpendicular lines, or by the right angle theorem. Therefore, we know those angles are congruent. So angle DAB is congruent to angle DEB because of the right angle theorem. So again, I'm leaving steps out, so this isn't something that you would write down necessarily. All right, and then you have that last part that's always helpful is the reflexive property, right? So I know that BD is congruent to itself, and those correspond with themselves. B corresponds with B and D with D. And now look, I've got the triangles are congruent, so I know that triangle BAD is congruent to triangle BED by the angle side theorem. So that's great and everything. And then why did I want to prove the triangles were congruent? Well, because then I have CPCTC. So I know that my last step of the proof would be, well, second to last, would be that I know AD is congruent to ED by CPCTC, and therefore I know that those are equal in measure by the definition of congruency. So super easy to prove that angle bisector theorem by using our congruent triangles. And that's why we talk about it after we do congruent triangles. So that's why if you're just given an angle bisector, because you can construct those perpendicular lines, make two triangles, prove they're congruent no matter what, you can always prove that these two segments are congruent, which means these are equal in measure. So on an angle bisector, wherever that point lies on the angle bisector, the distance between it and the sides of the angle will always be equal in measure. And remember, when I say distance, it has to be perpendicular because that's the definition of distance from a point to a line. Okay, so we looked at that in GeoGebra, and now we're going to look at the converse of the angle bisector theorem. So remember, converse is just swapping the hypothesis and the conclusion, but we have to word it a little differently here. So now we're just going to say, hey, I have this angle and have this point somewhere on the interior of the angle. If you remember, being on the interior of the angle has to be between when the interior of an angle is between 0 and 180, those angles, so like there's an angle around here, but that's greater than one angle, so we're always looking here. So the interior of the angle is any points inside that's like contained in this angle, and this goes on forever, so it has, you know, an infinite number of points. Anything over here is on the exterior of the angle. So we're saying that if you have a point somewhere in the interior of an angle that has some specific qualities, so it's in there such that it is equidistant, so the same distance from the sides of the angle. So again, since it's distance from a point to a line, it has to be perpendicular in order for that to be considered distance, and that's the length it's talking about. So if you have a point that lies on the interior of an angle where the distance from it to each of the sides are equal in measure, then this point must lie on the bisector of the angle. So the regular theorem says if you have an angle bisector, any point on it will be equidistant from the sides. This is saying if you got an angle, you got this point that's equidistant from the side, well, then it has to lie on the angle bisector. So let's go ahead and name these points so we can talk about them. We're going to do the same points. So we're going to name that D, and again, that will be A and C and B. So what I drew for you was the given, and what we're adding to it is the conclusion, which I forgot to mark up here. This was the conclusion up here that you had equal distance there and therefore congruent sides. But remember, the theorem gives you equal measures, and then we can get congruency if we need it. So down here, I gave you the given, and now we're going to add to it what we're concluding that, oh, hey, well, then this line that connects the vertex of the angle to that point on the interior that is equidistant from the sides, that must be the angle bisector. So then this has to be true. Then that's what you can conclude, is that that ray will split this into two congruent angles. So let's look at this here. So if AD is perpendicular to AB and DC is perpendicular to BC, and we know that AD is equal to DC, so it has to be perpendicular and these measures have to be the same, then we know that point D lies on the bisector of angle ABC. It has to. Cool beans. So one thing that's really important here is that and statement. Remember when we studied and or statements? Both of these need to be true in order for the conclusion to be true. So just because you have some point on the interior that is perpendicular, that there's a line segment between it that's perpendicular to both sides, so just this piece of information is not enough to prove that D is on the angle bisector. Likewise, just because you have a point on the interior and you have two segments that are equal in measure and the endpoints of the segment lie on the sides of the triangle doesn't mean that it is on the angle bisector. Both things need to be true. So let me show you a non-example for both. So my first non-example down here is, look, we have H, it lies on the interior of angle JLK, and look, here are two segments that are equal in measure. Okay, JH is equal to HK. But why is this not enough information to know H is on the angle bisector? Well, look, we can see, and it's not marked, so we can't assume, this is not a right angle. So this is not a right angle. So this is not considered the distance between H and side LJ. It's not the distance between this point and this line. That's what this is saying. If it's the distance between the point and the line, if those are equal in measure. Neither of these are considered distance because neither of these are right angles. So it really doesn't help that they're equal in measure. And look, if we draw it here, that's not an angle bisector. Now we can't always go by looks, but I made sure these measures were equal, and that's not an angle bisector. I have one more non-example, which is the fact that if you have it perpendicular, it still doesn't always work. So if I have an angle, and I've got this point, right, let's say it's right here. So obviously it's not going to be on the angle bisector, right? I can construct a perpendicular line here. So this right here represents the distance between point D and point C. And then I can construct another perpendicular line from D to this side. So if I construct, and I'm just freehanding it, but look there, how that there's no way that these two are equal in measure. This is the distance between D and this side of the angle, right? So this is A, this is B. So D lies on the interior of angle ABC. This is the distance between this point and the side of the angle. This is the other side of the angle. So this is the distance between this point and the side of the angle because it's perpendicular. However, I can't say this is on the angle bisector because remember, part of the theorem says not only is this true, I have AD and BA perpendicular, I have DC and CB perpendicular, but this also has to be true. AD has to be equal in measure to DC, but it's not. So that means I know that D isn't on the angle bisector. Both of these things have to be true in order to know that D is on the angle bisector. Otherwise, look, I gave you non-examples. There are possibilities where if those measures of from that point to a point on the side, not a specific point, meaning not the point that's the end point of a segment that's perpendicular, then it doesn't matter. It's not going to be on the angle bisector. If I have a point on the interior where I do have a measure of distance, but those distances aren't the same, then D is not on the angle bisector. So you have to have both of those things true in order to use that converse, okay? All right, so just a few more notes here, and then we'll do our second construction. So since a triangle has three, you guessed it, angles, did you know that? It also has three angle bisectors. So just like it has three sides and three perpendicular bisectors of those sides, three angles means you can construct three different angle bisectors in the triangle. Now, again, there's a point of concurrency for these three lines. So remember, I told you it was kind of crazy that when you draw the three angle bisectors in a triangle that they all intersect at the same point. It happens again with the angle bisectors. So the point of concurrency for these angle bisectors. So we're going to have a triangle. We're going to construct all three angle bisectors and they all intersect at the same point. And that point is called the incenter. So notice it's another center, and this is going to be a center of a different circle. So the orthocenter was the point of concurrency for the three perpendicular bisectors of a triangle, and it was the center of a circle that circumscribes the triangle. The incenter is the point of concurrency for the three angle bisectors of a triangle, and it is the center of a circle that's inscribed inside of the triangle. So this point is the center of a circle that is inscribed. So that means it's inside the triangle. That is, forms a circle inside the triangle such that, so not just any circle inside the triangle, but such that the center, so that's incenter, is equidistant, so the same distance from each side of the triangle, not the vertices. So that was the case for the circumcenter. It's the center of a circle whose distance is the same to each of the vertices of the triangle, but this one is this equidistant to the sides. So notice distance from a point to a side of the triangle has to be that right angle, has to be a perpendicular segment. So all three segments here are equal in measure. So this is, I'm just freehanding it here, that's going to be the inscribed circle, and this is called the incenter. So the incenter finds the point in the circle where if you draw a circle with that point where it just hits the side of the triangle, it will hit all sides of the triangle at a right angle. So it fits exactly inside that triangle. So that's the special quality of the incenter, is that it's the same distance to each side of the triangle. So let's go ahead and fill out the incenter theorem because that's all it is. So the angle bisectors of a triangle intersect at a point called the incenter. So this is the incenter theorem that is equidistant from the side of the triangles. So if I tell you that P is the incenter of triangle ABC, so remember we're talking about this outside triangle here. That's the triangle we're talking about. Then we can conclude that these distances, again, they're distances because it's a segment that's perpendicular to the side and goes through that point. So we can conclude that these distances are equal in measure. So I can say that PE is equal to PD is equal to PF. It really doesn't matter what order you put them in. But F, D, and E are all on the sides of the triangle, and from the center, in center to those points, it's perpendicular to the sides. That's why it's considered the distance, and they're all the same because again, that's going to be the radius of my circle. So you must know that. And also, I didn't have to explicitly say this was the in-center. You should have just known, well, you will, now that you know the in-center theorem and what point of concurrency it is for the three angle bisectors, then we could have known that P was the in-center without actually explicitly being told from this diagram. Because notice, we can see that BP is an angle bisector because it splits it into two congruent angles. We can see that CP is an angle bisector, again, there's two congruent angles, and AP is an angle bisector because it splits this angle into two congruent angles. So you should know that BP, CP, and AP are all angle bisectors here. And where they intersect is that point of concurrency called the in-center. So because it's the in-center, when you have a line that is line segment that's perpendicular to the side of the triangle and goes through that in-center, so there's three of them, one for each side, then all those distance are equal in measure. So I'm going to go ahead and mark that again. So we're going to use that fact to answer some questions. But let's go ahead and go to the next page and do the construction for the in-center.